Well, great. For our second speaker today, we have Nikolaos from Department of Statistics talking about mean variance equilibria in continuous time.
Thank you. Thank you, Mark, again for inviting me in this SPAAM seminar series, and thank you all for being here as well. So I'm going to present my recent project on mean variance equilibria, which is joint work with my collaborators Christoph Czichowsky from LSE, my PhD supervisor Martin Herdegen in Stats, and David Martins, who is a graduate from ETH Zurich. So just before we go into the talk, let me just say, so as you can see already from the title, the main thing is what we call mean variance equilibrium. So it's essentially a math finance application, maybe not something you hear very often. I'm not sure whether you are familiar with math finance applications. So again, it might be a bit hard to follow what are the standard modeling ideas in these kind of problems. So that might be a bit of a non-territory for you. And also the aspect of continuous time, which means that we model things in a semi-martingale setting. So again, you would be expected to maybe know some stochastic analysis. So either one side or the other side would help in understanding more details of the talk. But in essence, the mathematical idea, I would say, behind this whole problem is quite simple. It requires basic analysis. The idea is just in this particular framework, it's essentially far more technical, where we need to do certain things in using more advanced stochastic analysis. But the key idea is simple. So hopefully that you will understand on a high level what will be going on. So just to give you first the outline of the talk. So indeed, the central notion we look at is equilibrium asset pricing. So it's basically how to find the price process in which the market clears. So there is a market clearing condition which stands for the aggregate trading activity of the agents. So there are some agents trading the assets, and we want to find the price process under which the market clears. So that's justifying the notion of equilibrium here. And of course, the more difficult aspect is that we consider the condition that's also standard in this kind of equilibrium of optimality for each agent. So they don't just take arbitrary strategies, but they solve their own individual optimization problem under some utility function. And here we consider mean variance preferences, hence justifying the first part of the title. So we consider mean variance preference. Again, this will all be described explicitly later. So that's the idea. And I would also say that the interesting thing about the model is from the modeling perspective is we consider both financial and productive assets. So again, that will be described in a bit, but we have two kinds of assets here. And of course, it's customary actually when you derive the equilibria to look first on the optimization problem for each agent under a given price process. How would be the optimal strategy for each agent? So you get some insight of what is the optimal strategy based on the underlying price. And with that sort of problem, if you first kind of dig into that problem, then you would hope from there that you can derive the equilibrium. Of course, equilibrium is essentially harder, but that would be the natural first step. And then we will see in the, at least I will try to highlight in the individual optimization problem, there is a connection with quadratic utility. So the underlying optimal strategy for each agent will also be optimal for some quadratic utility. So again, it seems kind of abstract. The quadratic utility will somehow fall from the sky and will tell you that the strategy you're picking is optimal in a mean variance sense will also be optimal in a quadratic utility sense. So there is that connection there. And then therefore, you would want to hope that we can obtain the mean variance equilibrium through the class of quadratic equilibria as a fixed point. So that's what we do. So that's what I meant. The idea is simple. So we want to find a fixed point for a map whose fixed point exactly gives you mean variance equilibrium. That will be done within this class of quadratic equilibria. And of course, the non-trivial technical part to show is that this map is continuous. If it is continuous, then we can get existence of such a fixed point. So that's in a nutshell the problem without any notation. But again, just before we get into that, let me cite some partial, at least, literature on this CAPM equilibria. So capital asset pricing model is what CAPM stands. It's a more fancy notion of these models where mean variance utilities fall into. There is numerous literature on this work. So as you can see, it's an old problem actually since the 90s. But all of this work has been really done in one period. So you have time 0 and time 1. How do you obtain the equilibrium in that setting? Like I said, here we do things in a dynamic way, in continuous time. I highlight the work by Berg, which amongst all of these has, I would say, the most similar framework. They again consider these general mean variance utilities, and they have also an unhedgeable component in the market. Again, I will mention what that means. So that's the most similar, but of particular importance is the quadratic and linear mean variance equilibrium in continuous time, which is essentially the first piece of work by my collaborators that get equilibria for this type of utility. So we're going to go back to those results in order to get our fixed points. We'll rely on those results as well. And another branch of the literature that is important is the mean variance hedging problems. I just cited papers by Jean Blanc et al. and Probowinska and Schweitzer. Again, that's if you would be interested to know fundamentally the problems of interest that are linked to this problem, I would say those papers, they're very technical, but they sort of put together most of what we know in an individual sense, at least not in an equilibrium sense, about mean variance hedging. And the last thing is stability of quadratic BSD. So that's the technical component of the talk that I will emphasize towards the end, at least, maybe the last 5 minutes. It's stability of quadratic backward SD. So again, maybe you don't know what a backward SD is. I'm going to leave it at the end. I'm just going to say here that it's they arise quite naturally in math finance applications, generally speaking. And for that reason, they've been already studied in a I would say, quite deep extent. So the literature mentioning Brion and Huemoka Westry consider BSDs that have quadratic growth in the so-called control variable, which were the harder BSDs to establish. You first have Lipschitz type BSDs, just as you have forward SDs. That's the nice theory there. And the more difficult theories to establish when you have quadratic growth in the control variable. And again, this quadratic component comes from the quadratic variation of what cannot be fully hedged. Therefore, why there is this connection with quadratic BSDs, like sort of intuitively. But even with that literature, they don't quite answer what we want. So we need stability because we're seeking continuity. We need stability of some system. But it has to satisfy, the system has to satisfy the right growth conditions that align with the literature. So there is a missing piece that they don't have, that we require, that is somehow not, it doesn't quite fall into the class of BSD study there. So our contribution from a mathematical perspective is to prove a stability result where the underlying BSD system that we will have to argue stability of falls into. So that's sort of our contribution, which I will try to mention more explicitly at the end. So let's now just get into the model. So the financial market is given by filtered probability space where the underlying filtration is continuous. So i.e., all local martingales are continuous. That's what that means. And the interesting thing is that it need not be generated by a particular martingale. So in such applications in math finance, this filtration is usually generated by a process, and that's usually Brownian motion. So here, we don't necessarily assume that it's generated by a particular martingale. So that's where the agents cannot perfectly hedge the information in the market. So that's why this is an incomplete market framework. Sorry about that. And there are D1 financial assets. So So you're given the initial value and the martingale part of those assets, but we're trying to determine in equilibrium the finite variation part A. So that's what the financial asset is. And on the other hand, we have the more interesting productive assets, which basically, as their name suggests, they pay something here at the end, a terminal dividend, which is generally random variable, and the rest of the price process will be determined in equilibrium. So that's a distinction between these two assets. And just a side remark, we assume that each asset is a local to semi-martingale that's already condition satisfied for the financial assets. So it's more like a condition for the productive assets. So that's just a side remark. Don't worry about that. Let's just now look at what the agents are endowed with. To have k of them, and each of them has something at the beginning, an initial traded endowment, and we assume that it's 0, so eta kj is 0 for j from 0 to d1. So that means that for the financial assets, they don't get anything at the beginning, and the intuition for that is that those assets are kind of traded internally by the agents, so they're somehow, in a sense, fictitious assets. So it's without the loss of generality assumption here to say that this is 0 for the financial assets. On the other hand, they get at the end this total endowment, which is comprised by two components. First, the traded bit, which of course comes from the initial endowment multiplied by the terminal dividend, and then psi kn, n stands for the non-traded component. So again, and that's what they endow in total at the end. And we assume for mathematical tractability mainly that this whole thing is bounded above and below away from 0. But again, that's economically relevant. It's like an income. So at the end, you would expect that this is positive. And the terminal wealth of each agent is nothing else but what they have at the beginning, their gains from trading, so that's the stochastic integral from 0 to capital T, implementing a certain strategy theta in a self-financing way. I'm not going to talk about it because it's a necessary technicality, but you allow for nice strategies, basically, that don't allow external influence in the market. It's purely what you receive in the market, so you can have external or internal sort of injections in the price, in the value price of the agent. Plus, of course, what they're endowed, the non-traded bit at the end. So that's naturally what the terminal value of each agent looks like. And we just rewrite it in this way on the right-hand side, mainly because this is somehow only depending. So the only unknown here is basically, like I said, S is unknown, right? We're trying to determine an equilibrium. So the only unknown component of S comes through the stochastic integral, whereas here you also have S naught, which is not known. So this is a nicer way of writing out the terminal value of the agent, and they're trying to maximize that according to some functional here of mean variance preferences, which I describe in this slide. So it's a utility, so this function is a utility in two variables, the mean and the standard deviation. She's strictly quasi-concave, strictly increasing in mu, strictly decreasing in sigma, and it satisfies this bound. So up to here, so forget about these bounds, this is classically what the mean variance functional is. And now I'm just saying that it satisfies these bounds according to these parameters. So if these parameters were equal, first of all, this would reduce exactly to the linear mean variance functional, this popular choice. So what I'm saying, in other words, with these two parameters is like, I'm trying to quantify the breadth of the risk behavior of each agent through two parameters, somehow telling you how wide the risk behavior of the agent is through these two parameters. So economically speaking, that's how you can think of lambda min and lambda max, but they're also helping us mathematically to get the fixed point. And on the other hand, I also introduced the quadratic utility. Now this guy has an explicit risk parameter, gamma k, so it comes together with that. And I'm just mentioning the utility and the according problem because, like I said, there will be a connection with that problem between mean variance and quadratic utility problems. And lastly, to mention from the setup, the notion of equilibrium we're looking at is exactly finding the price process under which condition 1 is satisfied, which tells you that the underlying strategy of each agent is mean variance optimal according to this price process. And second of all, those same strategies satisfy this market clearing. So that's classically the notion of Radner equilibrium is called in economics. And the third condition is, again, for the same reason I mentioned at the beginning, is just a condition on the productive assets. So don't worry about that. What we're interested in is meeting these two criteria. And in light of condition 1, let's look at the individual optimization problem. So for a given price processes on the background, first I'm citing these mean variance hedging problems, which are of importance, again, to describing individual optimization strategies in mean variance sense. These are just telling you, first, mean variance hedging is essentially trying to minimize the expected square error between the gains from trading and the given pair of age. So that's what mean variance hedging is. And you have this extended version allowing you to choose optimally the initial constant, so the initial wealth if you want. So it's a pair now, minimizing according to both C and theta. And we denote the minimal expected square error of this guy by epsilon, age of S. So I add the dependence on S because S will not be a priori given in equilibrium. Now it's given, so you can forget about the dependence on S, but I have to highlight the dependence of those guys when we're in equilibrium. I'm also denoting the optimizers of these problems in a natural way, theta MVH, C and theta X. And we also have this triplet of coefficients. Again, this with respect to each agent K. And again, I'm not coming up with these coefficients. They're classical triplet of coefficients that are studied generally in mean variance hedging problems. Again, we will see that those coefficients exactly will allow us to characterize the optimal strategies for mean variance. So it's by no surprise somehow in the literature that we will need these parameters. So the other notion of importance is those of mean variance efficient strategies. So we cannot do any better in a mean variance sense. And again, you would expect intuitively at least that the optimal, if I have an optimal candidate for a mean variance optimization problem, you would expect that it satisfies this property. So if you have a solution to this problem, then it must be mean variance efficient. And you can even more establish that I can just rule out all other strategies and I can only consider optimizing over mean variance efficient strategies. So why are these strategies nice? So not only they're intuitive, we can characterize them in a nice way. So if you have a mean variance efficient strategy, you can decompose it in this way. So there exists a constant gamma k larger than this coefficient ck, such that you can write it according to those mean variance hedging parameters. You have this explicit essentially decomposition of the optimal strategy. And you also have D, I also highlight that with this same gamma k, this same theta, this is the unique solution to the quadratic utility problem, where this gamma k can be thought of as the risk parameter of the associated quadratic utility I'm picking. I'm picking that exact utility where this theta becomes optimal for that. So you have this connection. We can now put that together to solve the individual optimization problem for the agent. So this is now more fancy. Now, as we expect that the optimal candidate is mean variance efficient, so it would look something like the previous slide. But now, of course, this gamma hat depends on the underlying mean variance utility and this triplet of coefficients. And this gamma satisfies again these bounds, which are, as you can see, inherited from the underlying bounds that we imposed on the utility. So this is where these bounds are coming from. I will also say that this map is continuous. Again, this is not relevant for individual optimization. Who cares if the map is continuous? We have existence of an optimizer, so that's good. But it will be crucial property for the equilibrium. So just to also say that the way to get this gamma hat is not very difficult, right? You have the bounds, you have a fairly so a quasi-concave map. That's what I said at the beginning. The functional is quasi-concave. So with that and those bounds, there are key ingredients to get this existence of this guy. So again, it's just, I would say, a fairly simple continuity argument where you just need to know a bit more about quasi-concavity instead of concavity. So again, this is not particularly difficult or deep in any sense, I would say. But now with that in place, we can start looking at the quadratic equilibria. So this is the main result, one of the main results of the paper I cited earlier, where we can explicitly characterize for a given gamma bar. So by the way you get quadratic equilibria is via, again, this classical notion of the representative agent. It's the agent who holds everything in the market, the aggregate initial endowment, eta bar, and the terminal endowment psi bar. So, so we can basically look at a single agent who has those quantities, and for a given gamma bar, we can get explicit formulas for what the equilibrium S would be for each, the financial asset here and productive asset. And the underlying, what's called the martingale measure, the risk neutral measure Q, is bounded here. So it's quite a strong condition that doesn't often happen, but here it happens by the fact that we consider these guys to be bounded above and below away from zero. It's by no surprise that the random Nikodym density of the risk neutral measure happens to be bounded. So again, that's a technical remark for those who might know what a martingale measure is. So that's nice. We have an explicit decomposition for each gamma bar. So the idea now is to say, take an arbitrary gamma bar and look at the implied aggregate risk tolerance, this gamma tilde. So I take this as gamma bar. I look at what this triplet of coefficient is according to this as gamma bar, and then I consider the gamma hat UMV that comes from the individual optimization problem. So it's an iteration of maps, if you want to think about it like that, a composition of 3 maps that satisfies this. So this convex combination essentially satisfies these bounds. It's not quite trivial to see. You need some more analysis on mean-variance hedging, but that's the point. You start with a gamma bar, you end up with a gamma tilde, and this convex combination falls into those 2 bounds where these gamma max are given explicitly. So what's interesting to see here, quite obviously, is again, if those coefficients were equal for each k, the lambda min and lambda max, you would be back to the linear case, right? And the fixed point actually would be explicit, right? The fixed point would instantly be just this constant here. So the fixed point in the linear mean variance equilibrium is explicit. Here we're just generalizing exactly what they did in the earlier paper. Now the fixed point need not be explicit. It has to fall into this interval between gamma min and gamma max. But of course, the missing bit is continuity. It's not clear whether this composition of maps is continuous. So the first step, of course, is to maybe do a bit more work on the quadratic equilibrium to get nicer decompositions, so more unified ones. So a way where we can write the price process now for both the financial and productive assets all together, according to a base martingale n, which is a martingale that only depends on the model primitive, so there's just some notation, but the point is that it does not depend on the arbitrary gamma bar. So what you can see here is what have we accomplished with this decomposition. We've managed to basically get at the end here at 8 a decomposition where gamma hat only appears in the integrands not the integrators. So both the martingale part and subsequently its finite variation integrator do not depend on gamma bar. So from a technical perspective, it's sort of easier to get to argue continuity of the underlying S gamma bar if you only have coefficients who depend on gamma bar. So that's the point. So with all that, then, so that's the final, I would say, notation that we need. So first, I'm just needing a kappa n, which is the random nicotine derivative of the quadratic covariation n with respect to its trace. So that essentially allows you to write, now instead of a high-dimensional integrator, this is a univariate integrator. And here you have a matrix multiplication going on, but that's essentially an easier way of writing this earlier decomposition. And the second important notation is this space S. So this set of pairs psi lambda that inherit the properties from here. The only extra thing we add is the underlying density satisfies the so-called R2P inequality. So again, you don't need to know what that is, but why do we need that? Why is that important? Is so first, our densities, as I said, are bounded. So it automatically satisfies that inequality. But that inequality, in the literature, you can argue that those coefficients in the following slide, so as a family over these parameters, they're dominated in this BMO space. Again, I don't know if you know what the BMO space is, but it's essentially the martingales. So these stochastic integrals altogether, it's a martingale. It tells you that they are, so martingale is in BMO, is sort of the supremum over whatever time you restart with. So it's a dynamic, it's a dynamic condition that tells you that however you're gonna trade, so in a uniform sense, you can't make an infinite profit. So from a mathematical, so from an economical perspective, that's what BMO means. So you have a uniform condition that is sort of the next relaxation from saying, I don't want necessarily to have bounded coefficients. I want something a bit more relaxed, but again, control sort of the outcome of the trading horizon, again, by not allowing you to make infinite profits. So you can look up what BMO is in more detail, but again, that's technically what's crucial here. So we're ensured that this family is dominated in BMO, and with that you can establish that first psi1 gamma bar. So the first component of this decomposition of the map that we're looking at is continuous. So again, you need a nice metric for that, and it's a metric in an L2 sense that aligns with this BMO. So because you have this dominance, you can apply your favorite convergence theorems to get a continuity of psi1. Psi3, we mentioned at least the continuity in this earlier theorem. So the missing bit is continuity of psi2. So for a given pair psi and lambda n that converges sequentially, we want sequential convergence of this triplet of coefficients. And first of all, now we resort to one of the citations I had earlier on dynamic MVH problems, which tells you that this triplet of coefficients, now parameterized by little n, they can be described as the initial conditions of BSDs y2n, y1 and h, and y0 and h. By the way, here h is an arbitrary payoff, but you can plug in the endowment of each agent. So you can think of h as psi k.
Nicholas,
yeah.
1 minute.
Yeah, I'm finishing now actually. So that's the last slide where I'm just writing out these BSDs. So let's just look at the first one, for example, just to get the idea. So BSD has first the semi-martingale solution, y2, like forward SDs, but mu, the control, so this is the control variable, it's also part of the solution to ensure measurability. And then you have another martingale n perp that is orthogonal to this martingale nn. Again, that comes from the fact that we're working on these general filtrations. So it's a triplet of solutions. And the point is this green guy that is in BMO. where the literature that instead just assumes at best that you have some exponential moments, but BMO is not quite the same thing. So you have to prove a separate stability result for these BSDs. I'm not going to say anything more on that. I can leave it in the questions if you're interested to ask. But the point is, we can prove stability for these BSDs and essentially get continuity at 0 for these guys and therefore for this map, which was the last bit to get the fixed point. And you get the mean variance equilibrium from that fixed point. So that's what we've done. And the last thing that one can really do is work with some more challenging technically part where you allow for filtrations that are not necessarily continuous. So you can have discontinuities in the local martingales. So that's, I would say, what would be the interesting route to go down in these invariance equilibrium problems. But that's it essentially. And thank you. Any questions, feel free to ask.